Okay, in this video we'll take a look at solving a couple of problems involving conservation of mechanical energy, a little bit more involved than some problems that we've seen before. This particular one here is going to involve our spring-loaded launcher that we've done some things on in class, and then also in this video we'll take a look at this elevator problem. Let's go ahead and begin. The top equation here is just talking about including now elastic energy as one of our energy states that we can have for mechanical energy. And so this equation is basically saying our kinetic energy that we start with plus our elastic energy that we start with is going to end up changing in quantity, maybe different amounts of different values for kinetic energy and elastic energy, but when we're all done, what I start with is what I end with. So this is just a general statement, conservation of mechanical energy, now including elastic energy. Our spring-loaded launcher has an elastic spring in which we can do work, so that we can store that work as elastic energy. That spring has a spring constant of 650 newtons per meter. We're going to compress it 7.5 centimeters, so we do some work. When we do that, that work is now stored as elastic energy. And then we're going to use that elastic energy to then shoot that ball, 9.2 grams, and see how fast it should come out ideally. Now, in this problem, we're also going to look at what we actually got. You might remember when we did this laboratory work early in the year, we actually got a speed of 6.6 meters per second. We're going to compare that as an actual value to the ideal, so we can talk a little bit about efficiency. And then finally, we're going to use that speed of 6.6 meters per second, 35 degrees, to try to figure out how high it should rise. And then finally, we're going, and then when we're done with that, we'll go ahead and do some projectile motion problem here to determine how high it will rise if we shoot that at 35 degrees to the horizontal. So a little bit of review of some previous concepts as well. So let's go ahead and begin. If we consider a big idea on mechanical energy conservation is just considering where we want to start our energy analysis and where we want to end our energy analysis. So let's assume for this first part that we are starting with the compressed spring. And so we would say that the energy at this point is elastic potential energy. So use of E, I think your book might call that use of EL for elastic energy. Now, when we pull that pin and that spring pushes that ball out, by the time it gets to this point, now the ball is going to be traveling with some velocity, and that's what I want to find. If I consider this as my starting state and this is my ending state, then what I have now is all of that energy shown as kinetic energy. It's just an energy transformation. Right? So elastic is going to kinetic. So I take my general statement, MEI is equal to MEF. That's, again, a fundamental law of nature. If we have no non-conservative forces acting, no dissipative forces that's able to remove some of that energy and put it into non-mechanical forms, then we can use conservation of mechanical energy. What I'm starting with here is U elastic, and I'm going to end with kinetic energy of that ball. So 1/2 K delta X squared, that's the initial mechanical energy that we have. It's in the form of elastic energy. And when I'm done, it's going to come into energy of that ball, which we're going to say is 1/2 mv squared. My goal here is just to solve for the ideal velocity, how fast you should be coming out. And so let's just solve that algebraically. V squared, switch signs here, K over M times delta X squared. Take the square root, and we get that V is equal to square root of K over M times delta X. Let's go ahead and start plugging in some numbers here. 650 newtons per meter. That's actually pretty close to the actual spring constant for that spring. Divide that by, let's see, 9.2 grams. Well, that's the actual mass of that ball. But I better put that in kilograms here because the Newton is defined based on the kilogram meter per second squared. I got to make sure that those units are consistent there. Taking the square root there, that's delta X is outside of the radical now. 7.5 centimeters. I'm going to put that in meters. That way, when I'm done, I'm going to get a speed in meters per second. Let's go ahead and do some computation. Go through all that math, and my calculator is saying I should ideally get a speed of about 19.9 meters per second. So that would be the ideal speed of that ball. Now, we approached this problem assuming that this was true. In reality, when we go through and actually do the experiment, we see that we get a much smaller amount of mass out than what we should get ideally. And the reason for that, it might not be obvious, but we certainly have a little bit of friction inside of that launcher that's keeping that thing from coming out as fast as it should. The other thing that might not be as clear is that a lot of the energy doesn't actually go into the energy of the ball. The ball is certainly coming out at a high rate of speed, but a lot of the energy retains inside, stays inside of that launcher. That spring has mass. It takes some energy to change its motion as well. It's got inertia. And so, but that doesn't come out, right? That spring is sort of locked inside. And so we're not using any of that energy to sort of, the energy I use to move that spring does not go into that ball, right? So we're only getting some out, not as much as what we expect. So part B of this is to determine the efficiency. Let's go ahead and do that. Efficiency is defined as output work or output energy divided by input energy, or input work. Now, in terms of some variables here, let's go ahead and look at this. What I'm getting out of this is kinetic energy. I'm going to put that down as the actual squared, simply because it doesn't come out that fast. So I'm going to use the experimental actual value to determine what that is. Now, the input work was my 1/2 K delta X squared. That's how much work I did to compress that string together. So if I take that ratio, I'm going to get a measure of the efficiency. So let's see. So that I have consistent units again, I can get rid of those halves, but I better put this in kilograms, and then my speed actually is 6.6 squared, not 19.9 squared. K is 650 newtons per meter, and I'm sort of breaking good form here. I've got my units, but I know that if all of my units are SI units, then everything should work out. That the numerator and the denominator should have the same units throughout, provided everything goes back to the SI units. So 650 newtons per meter, and delta X squared, let's see, that is 7.5, so 0.075 squared. Okay, so let's go ahead and check that. I'm getting about 11% efficiency. Okay, so only about 10% of that energy goes into moving that ball. The other 90% either is wasted as heat or some vibration inside, or actually goes into moving that spring around. And if we ever disassemble that launcher, you can see that that spring inside is actually quite massive, especially in comparison to the mass of that ball. So only some of that energy comes out as useful kinetic energy. Now, letter C, that was A, this is B, and let's take a look at C. Letter C is really just a little bit of a throwback to the projectile motion stuff. I wanted you to see that we could handle projectile motion problems using energy principles as well. So let's go ahead and take a look at this. Again, when we're using energy principles, it's important to consider where I want to start my energy analysis and where I want to end my energy analysis. So I'm going to just look at this ball in various states here. It could be compressed inside of that spring, ready to be launched. It could be looking at it right after it comes out of the launcher. We could be looking at it right at the top of its motion. Now, clearly, since we're looking for how high it goes, this is going to be my final energy state. Right? So this is going to be ME final. Now, I have a choice. I could either go here and say this is ME initial, or I could say how fast, we know how fast it's coming out, maybe use this as ME initial. For this particular case, I'm going to go ahead and choose my energy state to be here. This is my starting energy, that's my ending energy. So when I equate ME initial to ME final, what I get is kinetic energy that I have initial is going to end up equaling, this is a little bit trickier. I'm not shooting that ball straight up into the air. If we're going straight up into the air, all of the kinetic energy would go away and go into GPE. Here, I still have some kinetic energy due to its horizontal motion. I want to be careful. Kinetic energy is not a vector. Right? It's not like I have kinetic energy horizontally, but I am moving horizontally, so I still have some KE due to its horizontal motion. I can't forget that portion. That's not the case if I shoot it straight up. Here, it still is moving with some velocity there. But I also have GPE, so gravity. Now I'm looking for how high it rises, so I'm really looking for the H portion of this particular equation. Let's go ahead and start putting in some of these values. 1/2 m V initial squared. That V initial is my 6.6 meters per second. That's how fast I shot that thing out. 1/2 m. See, how fast is it moving horizontally still? But I have to consider the fact that I got to use some of the other tools that we've developed over the course of this year. If this is V and this is 35 degrees, then I need to know how fast it's moving horizontally. V cosine 35 will get that for me. So 6.6 times the cosine of 35 is about 5.4 meters per second. So at the very top, it's still moving at a speed of 5.4 meters per second. Okay? And so I can put that in there as Vx squared, and then plus mgh max. Let's go ahead and cancel that. Now you notice, since I chose the starting energy as the point right after it comes out of the launcher, then the mass is the mass of that ball is in every one of those terms. I can cross it off. If instead I chose here, I would not be able to cross off those masses over here, and it might be a little bit harder for me to go through and do that. So for this particular problem, it was easier for me to choose this as my starting energy, and that being my ending energy. My goal was to solve for each mass. So let's see, 1/2 V initial squared minus 1/2 Vx squared is equal to GH max. I'm just going to go ahead and say it's equal to H, and then divide both sides by G. And now I can go through and finish up this problem. So let's see, I have 1/2 that's common in both terms, so I'm going to go ahead and just write that as a 1/2 V initial squared minus Vx squared all over G is equal to H. And for those numbers, V initial was 6.6, so square that. Vx, my final velocity at the very top, is 5.4. And then divide that by 8. I'm not going to drop my units here. I'm going to put those off to the side. This meters squared per second squared. I know that that's going to be the case for those. Those are all velocities. And I'm going to divide that by meters per second squared. Just a quick check on my units. I see that that does reduce to meters, which is what I was hoping for. And when I'm all done with that, I'll 0.73. So 0.73 meters. Okay, so how high it should rise. Take a moment and just consider some other things. If I had shot this thing at a steeper angle, right, so instead of 35 degrees, if I had chosen to shoot it more like 70 degrees, I would end up having less horizontal speed, which means when I'm done, I should actually have more of my energy going into gravitational potential energy because they don't have quite as much horizontal speed at the very top. And so that seems to be consistent with what we found here. And so just another thing for us to consider as we solve some of these problems, just to check to see what would happen if I adjusted my initial conditions. Does it make sense? Does it provide a consistent solution? And it seems to do. Let's go ahead and take a look at this problem here. It's last one. The video's getting quite long. Sorry about that. But here we have an elevator, 1,250 kilograms with people inside of it. Unfortunately, falls from a height of 35 meters. It's brought to rest with a safety spring, 66,000 newtons per meter. How far does the spring need to compress? And importantly, from a safety standpoint, what's the maximum acceleration of the occupant? So quite a bit going on here. Let's go ahead and consider this thing over here. We have this. I'm going to redraw this just so I can add some things to it. Here's the elevator. It's at a height of 35 meters above where the spring is. So let's go ahead and draw that spring like this. And certainly the spring is attached to the ground somewhere. But when this thing falls, really, unfortunately, by the time it gets to this point, it's going to be moving quite fast. Hasn't hit the spring yet, hasn't compressed it yet. So now I just have a different energy state where it's taken its gravitational potential energy, put it into kinetic energy here. And then when I'm all done, this thing's going to go down some distance. I don't quite know what that is yet. That's one of my goals here, to find that. And I've stopped at this particular point. Okay, so now this is important for you to understand. I no longer am moving, right? My kinetic energy has gone away. I do have elastic potential energy, but very importantly, I still have, if I choose this as my reference, I have some negative gravitational potential energy. So I want to be careful here. The distance that this thing compresses might be substantial, so I'm going to not ignore the changes in gravitational potential energy the object goes through when it starts to compress that spring. Okay, so sometimes we can ignore this, sometimes we can't. In this case, I'm going to choose not to ignore it and see if that makes sense when we get through it. Let's go ahead and start this with my basic principle of mechanical inertia conservation. If I choose this as my reference, then all I have at the beginning is gravitational potential energy. So U gravity initial. At the very end state, I could calculate its speed on collision here, but the nice thing about this is that I really don't need to. If all the energy stays the same, then I can look at the energy at any one of these spots and say that the total is the same as what I started with. So let's just skip over this intermediate state and go right to there. When I'm done, I have U elastic because I've compressed that spring, but I also have some final gravitational potential energy. Importantly, this value is going to be negative because I'm below my reference. Okay, let's go ahead and start to put in some of these values. Let's see, mg h initial is equal to 1/2 k. I know that value. But how far does it compress? Let's go ahead and call that x squared. Okay, so this distance right here is x. I'm going to end up figuring that out. So 1/2 k x squared plus mg. Now, I'm below my reference here, a distance x below. So I'm going to put that in as a minus x there to account for the negative potential energy I have at this point relative to where I'm choosing for my reference. Now, choosing my reference here allows me to know that value. HI is 35 meters. If I instead try to choose this as my reference, I wouldn't know how high up I'm starting with. So you have some choices as to where you want to start or where you want to choose your reference. Remember, it's only changes in gravitational potential energy that have any real meaning, so you're free to choose whatever spot you want. In this case here, it just made logical sense for me to choose the spring's initial location as my reference because I knew my initial height. Just can't ignore the fact that it's compressing some distance. Okay, so let's go ahead and solve this. I see I have an x squared, I have an x term, and I have this. I know all of this, but I do have a quadratic, so I'm going to go ahead and start to write this down in standard form. 1/2 kx squared is going to be minus mgx. Bring this over to the other side, minus mg h initial is equal to 0. And it might be just as well to solve this as a quadratic in x, just using the symbols here. So x is equal to the negative of b, will it be mg, right? Since b itself is negative mg, I just have mg for that. Plus or minus the square root of, b squared would be mg squared. Minus 4 times 1/2 of k. That's my a value there. And then let's see, minus 4ac, negative mg h would be my value for c. Two negatives there, so we're going to go ahead and make that just be a positive throughout. And then divide that by 2a. Well, 2a is just 2 times 1/2 k. So there we go. Let's go ahead and start plugging in some numbers and see what we get. A lot of math here. Plus or minus 23, 8, 21. So I lost a number. It's 238,212. Now let's do that 1250 times 9.8. You're like watching paint dry on your end. Sorry about that. All right, so I have two solutions for this. One of them is positive, one is negative. I'm going to use a positive solution, and the reason for that is I sort of considered that I'm going to consider the negative potential energy due to the x value. So I want to be careful there. If I use the negative value there, then this term here would end up being positive. Got to be careful there. I'm going to keep I'm going to do the positive solution. So 12,250 plus 238,212. Losing some digits there, so I might have some rounding issues with that. But that's the numerator. Then divide that by 66,000, and I'm getting about 3.795. I call that 3.8 meters. Okay, so that would be its compression distance. Okay, how far that thing's compressed. Now, 3.8 meters is substantial. It's, certainly, it's higher than the height of my classroom. So I'm not going to choose to ignore the difference in gravitational potential energy it has between these two states. 3.8 meters is significant enough. Okay, so certainly want to put that spring down here only a meter or two above the ground. It needs room to compress to be able to stop that. Now, part of the B on this is what is the maximum acceleration of the object? So interesting. For a spring, let's go ahead and draw an FBD here. At the very bottom, we have an mg, right, weight of that elevator, 1,250 kilograms times 9.8, and the spring itself is exerting an upward force equal to kx, right? And so since I have the compression distance, I have the force that that spring is exerting. First, this set of occupants are going to be accelerating maximally at the very bottom, upward. And that's what I want to determine, is what is that value? Now, important to understand that when they hit that spring, they're moving downward at a high rate, and they're only accelerating due to gravity. But as they compress that spring, there's going to be an ever increasing force upward to slow their motion. The acceleration is going to end up being a maximum at the very bottom. You want to be careful. You might need to actually have some sort of locking mechanism down here to keep them from bouncing back up like a pogo stick. So some way of sort of keeping them from flying back up due to that very large unbalanced force upward. But nonetheless, let's calculate that value for A. Of course, to do that, we need to go back to this second law. We can't ignore or forget some of those other laws that we've looked at from before. If I want to do a detailed analysis of that acceleration, the second law is where I need to go. So I have kx minus mg, and I'm going to divide that by the overall mass of that object. So kx, we got 66,000. Compress that at 3.8 meters minus, let's see, 12,250, and that was our value there. And then divide that by 1250. Okay. So let's go ahead and do that. 66,000 multiplied by 3.8. It's a pretty large upward force, 250,000 newtons. Subtract from that 12,250, and then divide that by 1250. We get about 190. 190 meters per second squared would be their acceleration. If I divide that by 9.8, just to get a sense of that, that's about 19 G's. But boy, it's going to be a lot less acceleration than if they just hit that ground without that braking mechanism. So there we go. A couple of different problems for you on conservation of mechanical energy. Hope you found this video useful.